Good day! So for learning task 3, we're going to answer several questions in Klein's Organic Chemistry 2nd edition. So without further ado, let's begin. Problem 11.59 states, the ring forming reaction below, initiated by heat, is believed to undergo a stepwise radical mechanism via the intermediate diradical shown. Propose a reasonable mechanism to account for the formation of the product from the intermediate diradical. So we have here our intermediate diradical, and we would need to determine the mechanistic steps to turn this intermediate diradical here to our product here. Now this is the overall mechanism that has transpired into transforming the diradical into our product, but we would divide this into easy and more easily digestible steps. Now the first thing that has transpired is that this vinylic radical here would form a bond from this carbon here, which is part of a double bond. So this double bond here gets cleaved, leading to the formation of this cyclic compound. Now since this bond is cleaved, that leads to the formation of a radical in this position of the aromatic ring. Now this radical here is stable and is resonance stabilized because it is now part of a benzene ring, therefore it can move to any place within the ring. So as shown in these resonance structures here, the radical can move from this position into this position and from that position into that position, since again it is resonance stabilized. Now in order for the aromatic compound to regain its double bond, there needs to be an abstraction of hydrogen. And hydrogen here is abstracted via a radical, which takes away this hydrogen here. In this case, there is an oxygen radical, which would form a bond with this hydrogen here that leaves one electron to this carbon here, and one electron from this carbon and one electron from this carbon would go on and reform the double bond in the aromatic ring. Now that we have our aromatic ring, we only need to address the radical on our oxygen here. And again, via hydrogen abstraction, this radical here would form a bond with this hydrogen here, which undergoes homolytic cleavage with this compound denoted by R. It can be any other compound, as long as it contains hydrogen. That leads to the bonding between O and H, giving us our product. Problem 18.76 states, numerous herbicides and fungicides are known to contain an acetylenic group. For example, compound A is a pyrimidinone herbicide that functions by inhibiting the accumulation of both chlorophyll and beta-carotene. During a synthesis of A, shown below, an inactive product was also formed, compound B, which was found to be a constitutional isomer of A, also containing an acetylenic group. The ratio of A to B was 1 to 4. A. Draw a plausible mechanism for the formation of compound A. B. Draw the likely structure of compound B and provide a mechanism for its formation. C. Explain why B is favored over A in this process. So we have here our starting molecule, and it was treated with these reagents, giving us here compound A and compound B. Now this is the overall mechanism for the formation of compound A, and again we would divide this into easy manageable steps. Now for the formation of compound A, our methoxide here attacks the hydrogen here, and that attack by the methoxide leads to the electrons being given to the nitrogen, giving us a nitrogen with a formal negative charge. Now this formally negative nitrogen would then attack this partially positive carbon here, since bromine here would be hogging all the electrons, making this bromine here partially negative and this carbon here partially positive. The nitrogen would attack the carbon, leading to the kicking of this bromine out of the compound, giving us this product, which is product A. Now the thing is that this anionic intermediate here is resonance stabilized, and it is due to this resonance stabilization that would lead us to compound B. Now this is the resonance forms of the anionic uh, intermediate. Now as you can see, since the anion is in a benzene ring, it's in a former benzene ring, therefore this negative charge can resonate within this ring here. It can go from this nitrogen to this nitrogen, and from that nitrogen it can go to this carbon here, and from that carbon it can resonate towards this oxygen here. Now the thing is, with this resonance structure contributes most to the compound, because the formal negative charge is in the oxygen, which leads to the delocalization of negative charge into the most electronegative atom, and that this here is displays aromaticity. Now from here we can form compound B. Now again, this negative here, the electrons here, the lone pairs of the oxygen here would attack the carbon, which is partially positive, kicking off the bromine, giving us this compound. Now this compound is compound B. Now comparing compound A and compound B side to side, compound B is much more favored because it exhibits aromaticity. Compound A here is not aromatic, while compound B here is aromatic. Since compound B is aromatic, it is more stable and it has lower energy. Therefore, compound B is much more stable to form, and thus compound B it can be found in greater quantities. Problem 19.85. Aminotetralins are a class of compounds currently being studied for their promise as antidepressant drugs. The following reaction was employed during a mechanistic study associated with a synthetic route for preparing aminotetraling drugs. Propose a plausible mechanism to this transformation. So we have here our starting molecule. It was treated by these reagents, giving us this final molecule, our product here. Now this is the overall mechanism, and again, we would divide this into more easily digestible parts so that we could easily understand. Now, from here, it was treated with aluminum chloride and an alkene. So, one would notice that this would undergo a Friedel-Crafts acylation. So, the first step in the Friedel-Crafts acylation is the formation of the complex, wherein the chlorine here would attack the aluminum, forming this complex here, with a positive charge on the chlorine and a negative charge on the aluminum. Since chlorine now is positive, it can lead to the easily kicking off of this chlorine atom, which leads to the carbocation. Now that the chlorine has been kicked off, there is a carbocation. Now this carbocation is attacked by the ethylene, leading to the formation of this compound here. Now there is a formal a carbocation here, so to compensate for that, one of the double bonds in the aromatic ring would attack, leading to a cyclic compound here, as shown here. Now since the carbocation is now on the benzene ring, it can resonate. So as shown here, it resonates within the ring until it gets to this position. Now this hydrogen here is then attacked by the chlorine from the aluminum chloride with an extra chlorine, leading to the formation of HCl and the retention of AlCl3 and the return of the aromatic ring, giving us this product. So that is it. Thank you and have a nice day.